Hello, Algebra 2. Today we're going to be looking at inference. The book, I believe, calls this significance of experimental results, which is a fine name as well, but I like to think of it as inference because that's really what the major surrounding field is. So let's take a look. So you should have this note guide in front of you when you're watching. If you're just watching on YouTube, of course, it's fine to follow along with us as well. So, statistical inference is the field of using a small group or a sample of measurements to infer the true value of some larger idea, some larger characteristic, or in statistics, the godly word we use is parameter. So we're trying to take a small measurement or a small group of measurements and infer something about the entire population at large. So that's what statistical inference basically is. The SAT, from what I've deciphered looking at their new practice tests, includes this topic. They don't include it very formally. It's kind of an informal idea where you'll have a table or some other form of data display, and it'll involve information about a smaller group, and you're supposed to kind of extend that or infer how that would relate to another group. Sometimes they just use a proportion or something like that, but I thought it would be a good idea if we just tasted a little bit of the actual formal field of inference so that we can start thinking about this main idea. There's a lot of subtleties and nuances that you'd need to take a full class in statistics like AP statistics or a college intro statistics class to really fully grasp the idea, but we're just going to be tasting the main idea today. So statistical inference is the field of using a sample or a small experimental group to try to infer something about a larger population. So one purpose of this kind of studying is to look at hypothesis testing. So hypothesis testing is used to determine whether an apparent difference in two groups is likely to be caused by some kind of random chance. It's always going to be random chance when you have measurements, or due to some actual fundamental difference between the two groups. And, statistical inference doesn't have to be limited to studying two groups compared to one another. It can be used in a variety of different applications. But that's the first example we're going to be looking at today, and I think it's a nice one to start with. So let's fill in this blank. So this could be the word actual or maybe fundamental. So before we actually get into that formally, let's kind of bring this back to the probability that we've been studying up to this point. So for example, consider tossing two different coins. So we've got two different coins. Let me just maybe draw a couple coins over here. So we've got coin 1 and then we've got coin 2. Maybe they are different sizes. So two different coins, we're going to toss each one 20 times. So we do that and we record what happens. One of the coin lands 19 times heads out of 20 and the other one only lands 11 times heads out of 20. So what we want to do now is think about what we've been doing with probability lately and use our knowledge of either permutations or combinations to compute those probabilities. Like how many times, how many different ways, how many different possibilities are there for those two phenomena to have actually occurred? So what's the probability of getting 19 heads out of 20 tosses? So think about this for a second, and if you're watching the video in my class, you might want to pause it. Think about, in this situation, does order matter or does it not? So I think you're just thinking about whether or not the coin appears as heads or tails. I don't see why order really enters that kind of equation. So the probability of getting 19 heads out of 20 tosses is going to be a combination. So I think in fact it's going to be 20 choose 19. So let's go ahead and compute that possibility. So it's going to be, of course, 20 factorial over 20 minus 19 quantity factorial. And then we've also got to stick that 19 factorial out here, right? So 20 minus 19 factorial is just going to be, this guy right here is just going to be 1 factorial, which is just 1. So I can kind of forget about that and just say 20 factorial over 19 factorial. Now, that's a pretty nice factorial calculation because it's going to reduce like this. So that's going to be 20 factorial over, well, you know what? I'm running out of room there. Let me just scoot this over. Let's go down here. So that's going to be 20 factorial. You know what? Let's write it as, doesn't want to erase for me, 1 second. So that's going to be 20 times 19 factorial, if we write it like that, over 19 factorial. So the 19 factorials will cancel, and I don't even think we need to get our calculator. We just have our answer. How many ways are there for a coin that's flipped 20 times to land heads 19 times? The answer is only 20 ways for that to happen. So let's compute the other possibility. I think order still matters here. I'll do this one in green. So now we're going to do, we're going to do 20, choose 11. So how many ways is there for that to happen? So we could do 20 factorial over 20 minus 11 is going to be 9 factorial. And then we'll stick our extra 11 factorial here. So this one I don't think we're going to be able to do by hand. Let's go to our calculator. So let me pull that up. And we'll do it right here. So I'm going to go 20 factorial. So remember, here's your factorial. And I'll divide that by 11 factorial times 9 factorial. And of course, you could have your calculator actually just do this combination for you, but I think it's better for us to get in there and get our hands dirty and work with the factorials. So there we go. It looks like 167,000 different ways that this can happen, 960 as well. So let's go ahead and write that down. So 167960. So let's consider this question, which is an inferential question. Do the coins appear to be fair, or does there appear to be a difference? And explain. So if you're thinking about this, it'd be a good idea to pause the video and try to answer it. Basically, those are really different numbers of possibilities. It looks like these two coins are definitely different. We have some mathematical evidence here. Is it really precise mathematical evidence written up in a formal way? Well, no, but I think you can clearly see that there's only 20 ways this can happen for us to obtain 19 heads on 20 flips, and there's like 167,000 ways to get 11 heads. That's much, much more likely. So I think that one of these coins, maybe if this one was coin 2, this guy must be rigged. He is unfair, or at least there's something fishy going on with him. I think we've detected a difference, so you could talk about that right here. Okay, so before we get to our first example and actually compare two groups, I want to go over a couple more vocabulary terms. So in hypothesis testing, we can create two hypotheses to describe either our sampled or our experimental values, our experimental results. So one of those hypotheses is called the null hypothesis. And the null hypothesis basically just states that there's no difference between the two groups or samples or whatever that you're testing, that there's no difference at all, nothing funny going on. And the other hypothesis is going to be the alternative hypothesis. Now, our textbook set of problems don't refer to the alternative hypothesis, but I'd like you to reference both on the problems. When you do the null, just go ahead and do the alternative. It's a good habit to get into. If we're going to be tasting inference, we might as well taste that much. All right, so you can tell that hypothesis testing is going to involve a hypothesis, so you should be thinking about the scientific method, right, which kind of starts with a question or questions. And then from there, this is going but way back to elementary school probably. So you start with a question, you make some observations. Most of the time those are going to be measurements, but you take some observations, and then you form a hypothesis. So this is kind of the spot we're at right now. And then you analyze the hypothesis. And I'm sure in elementary, middle school, or in other courses, you've talked about theories and stuff. That happens a way down the road. What I think you've never probably really done formally at all is kind of evaluate this hypothesis. You might have made this, so you might have done this part, but you probably did this extremely informally. And in this next example, we're going to still be sort of informal. We're going to kind of build into how to do this formally. Of course, you need a full stats class to do that in depth, but the point of today's lesson is to start thinking about how to do it. So this example has a medical researcher, and that medical researcher is testing a new gel coating for a pill. And they want to know if that affects how it's absorbed in the bloodstream. So down here we have 24 patients. They were put in two groups, and they were measured 30 minutes after they took a pill. And the results of their blood test are being measured in micrograms per milliliter. So that's just the units. So we have a control group and a treatment group, and here is how much of the drug was in their bloodstream 30 minutes after they took the pill. So just a couple ground rules about this experiment. The control group here would receive a fake pill. So what do you think that is called? I think that's called a placebo. And that's because some people react in a way that seems like they're being treated or that they're actually receiving some kind of drug or some kind of treatment, even though they really aren't getting anything that's active. So the treatment group is going to be getting the active drug. And in this case, they're both really getting a drug, but one's getting one with a special gel coating, and the other one we're just going to not put the gel coating on, and maybe we'll make it slippery so that they don't know the difference. Okay? So what are the null and alternative hypotheses for this experiment? So remember, the null hypothesis is one in which there's no difference between the two groups. So let's just kind of start out by saying that blindly. So there is no difference. You know what? I think I might just go ahead and grab my text box to do this to make it a little bit nicer. So there is no difference between, you know what, let's say what there's no difference in. So refer to the variable in context. You want to build these in context. So there's no difference in the time it takes to absorb the drug. We don't really know what the drug is here. It doesn't really matter. There's no difference in the time it takes to absorb the drug into the bloodstream between the control or the placebo group and the treatment slash gel group that's getting that special gel coating that we'd like to investigate. So the alternative hypothesis, we can be real specific here, or excuse me, we can take it a little bit slower. So there is a difference in the absorption, if I can spell, time between the two groups. So there we go. Fix that word real quick. All right, so there's our null and our alternative hypothesis. Now, sometimes an alternative hypothesis can specify that one group is larger, one group is smaller than the other. Sometimes we kind of just go for this two-tailed version where there's just a difference. It could be in either direction. So the way that we're going to do this first example and actually make a decision and answer this question at the bottom, do you think the researcher has enough evidence of a difference? We're going to actually make some box plots, and we'll decide whether or not we want to reject our null hypothesis from those. So if you're watching the video right now, we just went over box plots, at least in my class, in the last few lessons, just to review how to do this. That was the main point. Go up here and construct box plots out of this data. You could do that entirely by hand. I really recommend that, or you could even just use your TI-84, something like that, and use one variable statistics a couple times to come up with the values. Try not to just plug it into your calculator. So pause the video and draw those box plots. And you want to stack them on top of each other for easy comparison. It doesn't really matter which one goes on the bottom here, which one goes on the top. So what I've already done is put all the data into my calculator. So let me show you that. Let's clear out this factorial. So I went to Stat, I went to Edit, and I put the data into my lists. I've got the control group and the treatment group. And then I went into second y equals, and I turned both of these plots on. One of them is plotting the first box plot, and one of them is plotting the second one. So I'm not going to waste time, and I've zoom 9'd my box plots, so I have a nice picture. So here's what you should have in that spot right down below here. Okay, so let's think about it. Just looking at these box plots, this is a fairly informal way to evaluate the hypothesis again, but I think that in this case we can certainly manage to pull it off. And the reason is, if you look at these two box plots, they seem to be fairly different. In fact, they're very different. For instance, remember in a box plot, between this whisker and the edge of the box, you have 25% of the data, and then 25% from quartile 1 to 2, 25% from quartile 2 to 3, and so forth. So what I see here, in a specific sense, is that from this spot right here all the way over to the end of this whisker is 75% of the data. So basically 75% of the data of this box plot is entirely, or really close to, above all of the data from this box plot. And likewise, 75% of the data of this box plot down here, from the minimum to quartile 3, 75% of it's below just about everything. I mean, this overlaps just a tiny bit here, but it's pretty much below everything out of that box plot. So that says that basically 75% of the data in each box plot does not overlap. That, to me, is evidence of a difference between the two box plots. So that's what I'm going to say down here, something like that. So let's go and answer the question and evaluate our hypotheses. That's what we do in statistical inference. So I'm going to say I reject the null hypothesis. Because, remember, the null hypothesis said that there was no difference between the two groups, and we saw a clear and distinct difference in the box plots. So I reject the null hypothesis. There is clearly a difference between these two groups, which is evident in their box plots. If I wanted to be a little more specific about this, and since we're just doing this very informally, I probably do, I'm going to talk about the percentages of data that I observed. So in fact, 75%, and I should go back and think about this. Which one was which? Let me go grab my TI here. 1 second. In fact, one of them is clearly higher. It would be helpful to look at which one is which. I guess we could go and just look at the data as well for that. So which one of these basically is the higher box plot? I think it's the control group. So the control group is the one that received the fake gel coating, and this group is the one that received the real gel coating. So I'm going to remember that when I refer to it. In fact, I might just make a little note to myself up here in my drawing, like you're going to have this. So I had one box plot up here, right? And it looked like that. Then I had the other box plot down here, something like this, and it looked like that. And this one was the control or placebo group, and this one was the gel group. So that'll just help me to make sure that I make my statements about each group correctly. So in fact, 75% of the absorption readings or times. I just can't spell absorption apparently. Let's see if we can learn how to spell absorption. All right. Absorption times in the control group were larger / longer than the absorption, the test. I think I got it. Readings times in the gel group. And vice versa. So it's not like that has to be both ways, but you can see that 75% of these are below. Maybe that's not very specific. I could, of course, omit it. So the most important parts here are my decision is nice and clear. I've rejected the null hypothesis because it seems there is evidence of a difference, and I just want to state that in context now. So we have sufficient evidence of a difference in absorption times for these two groups. And there's all kinds of other little statistical nuanced things I could put into this statement, but I want to focus today on evaluating a hypothesis, right? You're either going to reject the hypothesis or you're going to fail to reject the hypothesis. So that's the only other conclusion you should be saying. Either I reject or I fail to reject. You shouldn't be saying things like I accept the alternative or something like that. All right, so let's look at another example. So before we go on to this other example, I just wanted to say a few more things. So rather than simply eyeballing the box plots to detect a possible difference between groups, statistical inference has many different tests or specific, precise mathematical procedures to decide whether or not you should reject a null hypothesis. So we did that last one pretty informally. In this example, we're going to use one of those specific mathematical procedures, and it should relate to ideas we've been studying recently. One of the most basic of such tests is called the z-test. And there's actually a variety of different z-tests. We'll now use this test, one of those z-tests, to compare the mean from a sample to the mean of an entire population. So what I want to make clear is that in our book assignment, there's really two different kinds of situations that you're going to be given problems on. This one is not two different samples. This is going to be a one sample or one group test. The other one, of course, we had two different groups. We had the control group and the gel group. We evaluated that one informally. This one, we're going to use a mathematical procedure to evaluate one group. And we're going to be comparing its sample to the parameter of the population. So to find the z-value, that mathematical precision value that we need of a particular statistic, of this particular situation, in fact, you need to know both the sample average or sample mean. I think we've been using that recently. We called it x bar, right? Let me get that down below a little better. So what should go in this blank is x bar. We also need to know the standard deviation of the population. We've also been using that symbol recently, which is sigma. So we need to know both those things. Now, in reality, it's pretty rare that you actually know the standard deviation of a population, but we don't want to get too in-depth into this large field of inference, so we're just going to assume that for these problems. So once you have those two things, what's the mathematical relationship that is formed by z? So z then, the way you're going to compute this is you're going to take your sample average, you're going to subtract the population average that you'd like to test. So this guy right here, this mu, is also an average. This is the hypothesized value of the mean. So this is the hypothesized population mean. That's the thing we're going to be testing in our hypothesis test, right? And then what you're going to do is divide that by a standard deviation, sigma. So this should look familiar to you. This is the same kind of formulaic setup that we use to evaluate outliers when we wanted to use the mean method rather than the fences method. We also need to do one little other thing here and divide that by the square root of our sample size. And I'm not going to get into why that is. That would take a long time, and we just don't have that, unfortunately. So when that z value is close to 0, we don't have any evidence of a difference between the two things, the sample and the population, x bar and mu. But when that thing approaches like 2 or 3, isn't 3 the criterion we used to evaluate whether or not a piece of data was an outlier? I think it was. Once you get to 2 or 3, that says that what you're seeing is pretty unusual. We don't want to say it's an outlier. We just want to say that our hypothesis was wrong. In fact, the x bar and the mean, they're really not the same. So to be really specific for today, if the absolute value of z is greater than 1.96, that means if you have like a negative or a positive value, and it's pretty big, if it's greater than 1.96, then you can reject the null and you can be 95% certain that you've done that correctly. So let's look at a second example of this situation. So in this one, a tax preparation company claims to be able to give their customers an average refund of $3,000. So we go and we check them out. Pretty relevant lately because if you watch the Super Bowl, you can see how many different tax preparers advertise. So they make large claims like this one, this time claiming that they can get you $3,000 on average. So we go and evaluate them and see whether or not they're telling the truth. So we have a sample of 40 clients that we go and look at, and the average refund from this sample was only $2,600. Still pretty good, but looks like it's below $3,000. Then we look at all the company's records and get this 300 number. That's how much spread out they are. That's the true value of the standard deviation. We'll need that for a formula. Kind of unrealistic, but I guess you could look at all their records. So what we want to know is the company telling the truth? Can we reject their claim or not? So again, we're going to form a null hypothesis and an alternative hypothesis. So let's do that first. So in the null hypothesis, let me get my cursor there, we want to talk about how there's no difference. So they actually made a specific claim here. It's not like we have two groups. They made a specific claim about the $3,000. So we're going to say the true average refund, you can see I'm putting it in context, the population for anyone who goes in, that's what we want to hypothesize about. The true average refund for a customer of this tax company is $3,000. That's the null hypothesis. So then down here we'll say the true average refund for a customer of this tax company is, and we could just say simply that it's not $3,000 or it's other than $3,000. But in this case, since we've already got a sample that's $2,600, and since I really want to know if the company's cheating me, I think I'm really interested in, is it less than $3,000? So I'm going to change my alternative a little bit on this example. All right, so instead of doing this visually this time, we're going to use our new Z test statistic. And we'll follow the same formula that we had up above. We'll bring it back up. So we're going to say Z for us in this situation is going to be our average. The average we found from our sample was 2,600 when we looked at those 40 customers. We're going to subtract the hypothesized value, or the claim that was made in the hypothesis right here. This guy was mu. That's not m. That's the Greek letter mu. Tried to do it well. And we're going to divide by the standard deviation. Well, we already identified that. That was that 300 number we got from looking at all their records. And we'll divide by the square root of how many records we sampled. All right, so then we put that in our calculator and try it out. So I'm going to actually do this in the calculator rather than just tell you, and you should follow along and try it first. So I'd pause and try to put it in your calculator first, because there's a lot of opportunity to mess up here. So I'm going to put this in my calculator a couple different ways. I'll try to make it right up here so you can see. So one thing I could do is I could go and press alpha y equals and grab my fraction. This is the safest way to do it, and do it all in one shot. So I'm going to do it that way first. And then down here I could grab another fraction by going alpha y equals and go 300. And oops, wrong thing. Oh man. Well, I have to go down a little bit. Okay, second square root and 40. So that looks exactly right. So the value of z in this case is negative 8.43. I bet a lot of you working with your calculator could have come to a different answer. And that's because if you do it piecemeal, you have to be a little more careful. So let me try to do it one piece at a time, like so. And I'll get this answer first, and then I want to divide that answer by 300 over the square root of 40. If you do it that way, you'll see that the answers don't match. Negative 8.4 is not negative 0.2. So where's my mistake here? So if you're watching, you may, of course, have already caught my mistake, but my mistake is in order of operations. Right here in this line where I went negative 400, the answer, divided by 300, divided by square root of 40, it's basically flipping that 40 back up on top. Or in other words, computing something that I didn't mean. In order to do this piecemeal, you have to be more careful. When you get this answer and divide it by the rest, you're going to have to wrap the rest of it in parentheses so that your calculator knows that you mean to divide by that entire quantity. So that's a really common mistake I see Algebra 1 and 2 students making. So just be careful. And there you go. You can see we get the same value of z if we do it that way. So negative 8.43 is our value of the z statistic. So let's write that down, negative 8.43. Now remember, we talked about when we were doing outliers, if this value was more than 3, it's an outlier. And today I said if it's bigger than bigger than 1.96 in absolute value, so we better find its absolute value. which is of course just 8.43. That's way bigger than 1.96. So from that we can say that what we're seeing is really unusual. It's really unusual if we look at 40 customers in this situation for us to have if for us to have a value for the average of $3,000. It's just basically not going to happen. That's basically saying it's impossible. So let's answer and finish up this example. So can we reject the company's claim? I'm going to say typing does not want to work. We reject the null hypothesis. There is strong evidence, not only a little bit of evidence, that 8 number was way bigger than 1.96. There is strong evidence that the true average, and you can see I'm just going back up here to my hypotheses to guide me. The true average refund for customers like these, at least, maybe other customers are different. Hopefully we sampled our customers appropriately, but that's a whole other story. There is strong evidence that the true average refund for customers like these is less than $3,000. The company is lying. And there you go. So there's a small taste of statistical inference. I hope you found it powerful, because a lot of modern society's truth claims are based on this, and of course parts of the scientific method rely on this kinds of analysis as well. I'll see you next time.